So delta G at 25 degrees Celsius, we can do the same exact thing. We can calculate our change in our delta G of our reaction under standard conditions is equal to the same thing, our products, but in this case, our G value, our Gibbs free energy, minus our reactants. If we were at some other temperature, we would need to use our enthalpy, our delta H, and our entropy along with whatever temperature that is, right? If it was 25 degrees Celsius, we wouldn't have to do it this way. We could just go ahead and calculate delta G as above. Or what we could do is we could add all of our different reactions together. So this is kind of like Hess's law, right? Where we add several different reactions together to figure out what our total delta G is. So, apologize. One possible step for the formation of acid rain is this reaction here. Calculate delta G, it says at 25 degrees Celsius. Okay, so that's easy enough, right? And determine whether the reaction is spontaneous. Well, if we look back, our ways of calculating at 25 degrees Celsius, let's see, we could do it this way, but they didn't give us our G's values for each of our reactants and products. So I guess we can't do it that way. They did give us some H value, some S value. So it looks like we could do it that way with 25 degrees Celsius. But they didn't give us different reactions, so we can't use that. So it looks like we do have to use this middle reaction here. So as you can see, there's 3 different ways. Just kind of look at the information you have, pick out what you should be using. So here we go. They gave us delta H's. They gave us S values. So take a look at those, and you would need to calculate each, right? Because the reaction says it wants the change in the reaction of H and S, right, times T would give you the change of delta G in your reaction. So the first step would be, let's look at our table. Let's find delta H of our reaction. So once again, this is products minus reactants. So you're going to do your products are SO3, right, minus the sum of your reactants. So SO2 plus 1/2, right, because you got a 1/2 of oxygen, O2. You can go ahead and plug everything in, so make sure you plug it in directly as it is. I would probably go ahead and solve each component, right, and then take your products minus your reactants. So what you should get is negative 98.9 kilojoules is your delta H of your reaction. You're going to do the same thing for delta S. Sorry. Delta S, same exact idea, right? The equation should look almost the same because your moles hasn't changed. We're just now using our S values. So plug in your S values you got from the chart. And here we go. We got delta S is negative 94 joules per Kelvin. We can then go ahead and plug it in our equation, right? Because we have this equation here. The only thing we do need to remember is that our temperature needs to be in Kelvin. So we were at 25 degrees Celsius, right? Add 273, so we're at 298 Kelvin. One other thing we need to remember, if we look back at what our delta H value was, it was negative 98.9 kilojoules. Well, that's kilojoules. S is joules, so you need to make sure you convert. So here they converted the delta H to joules, and they ended up getting, right, they plugged in delta H minus your temperature times your delta S value. That allowed your kelvins to cancel, right, with your temperature, and then you had joules minus joules. So it ended up being a large number, so they converted it back to kilojoules. So delta G is negative 70.9 kilojoules. When delta G is negative, that means that it is spontaneous. So this is a spontaneous reaction. Here's another one. So they're saying this reaction that we used in the last example, estimate the value of delta G at 125 degrees Celsius. Is it more or less spontaneous at this temperature? Well, normally we think, well, if we raise the temperature, it should be more spontaneous. So let's see. So let's go ahead and plug in, as we already had these values, right? We already solved for delta H, we already solved for delta S. We're now plugging in our new temperature, 125 degrees Celsius. So 125 plus 273, we're at 398 Kelvin. So let's plug in that new temperature and solve. So let's see. We're at a new temperature, right? We got a negative 61.5 degrees, which is less negative, right, or more positive than that we had at negative 70.9 kilojoules. Therefore, this reaction is actually less spontaneous, right, because it ended up becoming a more positive value. It got closer to 0. Therefore, at an elevated temperature, this reaction is actually less spontaneous. So we can compare it, right? The more negative number, the more spontaneous it will be. So when we talk about our free entropy of formation, our free energy of formation, we can talk about our delta G, which is the change in energy when we have 1 mole from its constituent elements. So our free energy of formation of any pure element in their standard states is going to be 0. So this is very similar to our delta H of formation that we did last semester. So there are some 0 values for G. When we get up in more complex things, right, there is going to be some G value. They can be negative, they can be positive, it will vary, but once again, you will be given a table. The equation is almost the same, right? Except now we're using free energy. So, ozone, it wants us to calculate our G of our reaction. So we can do the same thing that we've been doing, right? First, you would have to find your table, find your values, make sure everything's in the right states, right? Make sure you have the gaseous form for all of your components. So then you can go ahead and write your reaction. So delta G is, once again, products minus reactants. So we have first our products, carbon dioxide, plus 2 waters, right? Plus 4 O3s. All of that is going to be added together. Then you're going to subtract your reactants. So CH4 plus 8 O2s. You would then plug in your delta G values for your reactants. I would go ahead and solve reactants and products separately, right? So you get products minus reactants. Here, this is a positive value because technically they have a negative here, another negative here, right? That ended up becoming a positive. So they ended up getting a positive over here for the reactants. You add them together, their delta G was negative 148.3 kilojoules. A negative delta G value means that it is spontaneous. So this is a spontaneous reaction. A reaction can also be talked about in the sum of delta G values of individual reactions. Remember Hess's law. We can add all of our reactions together. All we care about is our final state because delta G is a state function. So therefore, if we reverse a reaction, we're going to change the sign of delta G to the reverse. If we multiply our amount of materials, if we multiply a reaction by 2, you need to multiply delta G by 2, okay? This is exactly the same as Hess's law, except Hess's law, right, was with delta H. This is with delta G. We're just repeating pretty much everything that we did back last semester. So here's a reaction. We're trying to find this top reaction. So the 3 carbons plus 4 hydrogen gases gives us C3H8. Here's our following reactions. So what do we need to do in order to get this reaction at the top? So we can look at the individual components. I can look at this right away and say, let's see, this first reaction, it has C3H8 on the left, right, of the arrow. I need it on the right of the arrow up here. So I'm going to flip this first reaction. That would end up giving me a positive 2,074 kilojoules. Once I move down here, let's see, this reaction, it's got one carbon and I need 3 carbons. So it looks like I'm going to have to multiply this reaction by 3. So I would multiply this, negative 394.4, multiply by 3, and get some number. Down here, I got 2 hydrogens, but I really need 4 hydrogens. So I would need to multiply this whole reaction by 2, right, to get 4. So multiply this by 2 would multiply my delta G value. I would then add all of my reactions together and see if I ended up getting this as my total overall reaction. So let's see how they did this. Their first step was they took, the first reaction. So the first reaction, they saw C3H8 was over here. They know that they need it on the right, so they flipped it. So this is equation 1, right? But it's just flipped. It's the opposite. So their delta G value is 2,074 kilojoules. The next reaction, they multiplied it by 3 because they needed 3 carbons. So they multiplied it by 3. So once again, when you multiply by 3, though, that means you're multiplying this carbon by 3, this oxygen by 3, this carbon dioxide by 3. You're then also multiplying your delta G by 3. So they multiplied 3 times negative 394.4 and got 1,183 kilojoules was your delta G of your reaction. The next step, they need to multiply the bottom reaction by 2, right? So multiply H2, there's 2 of them by 2, multiply the O2 by 2, multiply water by 2, right? To multiply delta G by 2. So you should get negative 914.2. So here we go. They multiplied everything through, right? Everything's there. They got their delta G values. Now they're crossing out the same things on both sides. So let's look up here. Here we have 3 CO2s. Over here on the right, we also have 3 CO2s. So they cross them out. On the left, we have 4 waters. Looks like down here we have 4 waters. So they cross those out. Also on the left, we got 3 O2s, but we also have another 2 O2s. So we got 5 O2s on the left. We can cross those out with these 5 O2s on the right. So once everything's crossed out, we just write what's left. So we got 3 carbons, we got 4 H2s, and we got C3H8. So now we've added all of our reactions together. We can add all of our delta G values together. Delta G is now negative 23 kilojoules. So delta G is negative, so this is a spontaneous reaction. So here's a for practice example, 18.9. Please do this on your own and then double check. Make sure you got the right answer.